Good morning, chemistry fans. Mr. Fairbar and I were just finishing up a great conversation of all of our favorite movies. So hope you guys are having an opportunity in all of your studying for AP chemistry to stop and relax and watch some good movies, whether that's a nice romantic comedy or just a straight up comedy or maybe an action film. There's lots of good stuff out there. So make sure you're taking some time for yourself to do that because there's lots of good stuff out there. Today's chemistry lesson is a continuation of what we've been working on. I'm Mr. Byrne from Glenbard West High School. Today's Thursday, April 16th, 2020. I think we're wrapping up Unit 5 today on kinetics. We're going to be looking at a number of, finally look at that collision theory like I was mentioning on Tuesday, and then talk about how catalysts are going to affect some reactions. So we got another great resource to share with you, and some good problems for us to practice between today and tomorrow. Just remember that all of your questions, or if you still have some questions for you, your teachers, any high school administrators that are on here, you probably want to take a look at apstudents.org/exams2020 for any of the topics along the right hand side of the screen there. We're going to keep our focus on Thursday, May 14th. So we passed the 1 month mark a couple of days ago. Now I think we're at the 4-week mark because it should be exactly 4 weeks from today on Thursday. Remember that you're going to find the time that is in your local area, and we'll all be taking the test at the same time on the same day on our own individual devices. Okay, that exam is going to have completely free response format. You'll have 2 specific questions that you need to look at that will really be focusing on the skills of explaining chemical phenomena, drawing conclusions, analyzing systems, and supporting your claims with evidence and reasoning. So we're going to just continue to hammer those skills with you as we go through each of these lessons. Okay, our lesson overview is the same as usual. What you need to know in guided practice will be the meat of ours, but we'll start with our warm-up and then we'll leave at the end of class today with a couple of problems from retired AP tests for you to look at. Encourage you to stop and go grab a piece of paper and a pencil and maybe a calculator if you have one handy, so that we can talk about these problems in real time. But anytime you need to review or I go too quickly through something or what I'm saying doesn't make sense, go ahead and listen to it again and see if you can figure it out. Okay. So these are the topics that we're going to hit. Like I said, we're wrapping up Unit 5 in kinetics, where we're looking at, the heart of all of this is really a deep understanding of the collision model. And I think it's going to feel very comfortable for you once we can get to talking about all of the parts of it. But anytime we talk about collisions, anytime we talk about a chemical reaction, you really have to be looking at the collisions of the particles with one another. And so making sure that we have that at the forefront of our brain as we're moving forward is going to be a really important thing, whether it's talking about reactions or rates or mechanisms or any of that stuff. Okay. And then we'll wrap up by looking at how catalysts affect a reaction, a big part of what happens with chemistry in the real world. So that's really important, okay? So we're gonna start with our warm-up and we're gonna do something a little bit different today because those of you who were paying attention to our lesson yesterday may have noticed that the second equation that we talked about, right at the end, I made kind of a big error. And so a shout out to Crystal in New Jersey who emailed me and said, Mr. Byrne, I don't think that this makes sense. And it turns out that my work down here at the bottom was correct, but I think that I had made a couple of typos in step number 2 equation. So I think that the arrow was in the wrong spot. I don't know what I was thinking when I was doing that. So thanks for keeping me honest, Crystal. And those of you that were confused as we were going through this example yesterday, go ahead and take a screenshot of this, and we would come to the same rate. We come to the same answer down here at the bottom of the screen. It just, you probably had a hard time getting there, not having this equation correct as it is on here. All right. So let's get to our 2 homework problems as they were assigned from yesterday. The first one was kind of a backwards mechanism problem, right? So really taking our skills out for a ride and seeing if we are able to not predict what the overall reaction is, but surmise from the overall reaction and one of the steps what the other step would be. And in particular, it's probably going to be important that we are identifying step number 1 from the overall and step number 2. Because we're going to have to identify what are our 4 parts of a reaction. You might want to review that from yesterday. We can have products, we can have reactants, we can have an intermediate, or we could have some catalyst in there. So you could, anytime you have a mechanism here, you might want to review those 4 parts. So my analysis of this would kind of start, and I'm going to just go through each of the chemicals that are in the overall reaction and see where they came from. And if I don't have a clear spot where they came from, i.e. if it didn't come from step number 2, well, then we're going to say it must have come from step number 1. All right. So the first substance that I'm going to look at here would be NO2 gas. And so what I notice is that in the overall reaction, I have some NO2 gas, but for some reason I have some NO2 in the product of step number 2. So the only way to get to have some in the overall reaction, because remember, we're going to add together step number 1 and step number 2 essentially to get to the overall reaction. So the only way that we would be able to do that would be by having 2 NO2s in step number 1. So that these 2 NO2s in step number 1, when they balance out with one of the NO2s in step number 2, would leave us with a net of 1 NO2 in the overall reaction. Okay. Our carbon monoxides, COs from the overall reaction, we have 1 up there, and then we have 1 in step number 2. So between those 2, that is accounted for. So we're going to leave it alone. We would not expect that would come in step number 1. We would look at NO, nitrous oxide gas, and we would see that that is nowhere to be found in step number 2. And so we're going to need to include that in step number 1 as a product. And then just like with carbon monoxide, we see the carbon dioxide appears in the overall reaction and in step number 2. So we would leave it there. The last thing we need to consider is NO3, nitrogen trioxide. How did that get there? Well, it turns out that that's going to be an intermediate for between step number 1 and step number 2. And if it's an intermediate, what we know about intermediates is that they are used up in step number 2 because they were produced in step number 1. So we would put that on the product side of step number 1. And that gives us our complete reaction. And so our solution to this problem would be that we have 2 NO2s react to make 1 NO plus 1 NO3 there. All right, I'll give you a second just to process that. And then we'll go into our AP exam practice where we were given the reaction of 2 NO2s that are reacting to make 2 NOs and an O2. This happens at elevated temperatures. We've got a lot of different information. What we want to look at is the fact that we have graphs that are represented from this information, or graphs that came out of the experiment. And the first question asks us to explain how the graphs indicate that the reaction is second order. And so we would zoom in here and we should immediately recognize that this is our linear equation. And so because the linear graph of 1 over the concentration of NO2 versus time is a straight line. I'm sorry, the graph of that is a straight line. Then that indicates that it's a second order reaction. I want to caution you here to remember that we're always looking for the linear reaction, and we do need to know what the axis, what the y-axis would need to be in order to indicate if it's a first or a second, a 0, a first or second order reaction. Okay, and a couple other examples, we saw that they were listed. The first one listed was first order. The second one listed, sorry, the first one listed was 0 order, then first order, and then second order, right? And so we could just maybe assume because it was listed second that means that it's first order. And that would not be an appropriate way for us to analyze this data. What we want to do is really find the one that is the straight line. Here we've got a curve, here we've got a curve. This is a straight line with a positive slope. And then we would want to look at what is the y-axis here, and we know that 1 over the concentration of a reactant tells us that it's second order, not 0 or first order, okay? And so if we've identified that it's second order, we can write a rate law that is consistent with that. The rate is equal to K times concentration of NO2 to the second power. all right? And this is just a review, I think, of some things that we did on Tuesday, if I remember correctly. And then this is a review really of what we did yesterday. So we're going to look at two different mechanisms. This first one, I think, was pretty straightforward. If we've identified that this is the slow step, okay, we know that if we have a mechanism, this slow step that is consistent with a rate law that we wrote in part B. So we wrote here that the rate is a second order with respect to NO2. So we want to see, does this step, is it consistent with that? Well, we have two NO2s reacting with one another, which for an elementary step would be second order, right? And so our answer here would be yes, we've identified that step one is slow. So it's a rate determining step. So there we go. There we're using some good terminology of rate determining. The rate law of this elementary reaction is rate is equal to K times, it's very similar to what we wrote earlier, exactly the same as what we wrote earlier. And so that's consistent with the second order rate law. Okay. Second one is a little bit more complicated, right? Because we have one of these fast equilibrium problems. And so our initial reaction would be, our initial thought might be to jump to step number 2 and to say, oh, hey, this is the slow step of the reaction. The slow step just would be first order for N2O. And so that seems like it's inconsistent with what our rate law was in part number B. However, there's two things we want to remember. A, the fact that this is an equilibrium, and the people who wrote this problem were nice to us. They even reminded us up here that this was fast equilibrium, and that N2O4 is an intermediate here, right? It is produced here, but then would be used up again in step number 2. And we would never want to have N2 in a rate. So what we're going to say is that as an intermediate, it can't appear there. So we're going to have to do a little bit of math to prove that, yes, this is a possible rate law, or this is a possible mechanism, and we could come up with a rate law that matches what our answer was from part B. And so this is where we'll do a little bit of that fancy math from before, okay? And I've double and triple checked this, but call me out if we made a mistake here. But for step number 1, we know that if it's equilibrium, the forward rate is equal to the reverse rate. We're going to start a conversation of equilibrium, I believe tomorrow, but maybe next week, where we talk about, that's one of the fundamental principles of an equilibrium, a reaction at equilibrium, is that the rates have come to equal one another. And so we can say that the forward rate is equal to the reverse rate, and then we do that just solve for the concentration of N2O4 and plug that into our original rate over here. Okay, so we would say that the rate for this overall reaction gives us kind of a new, much more complicated K, but it would be some sort of a constant here times the concentration of NO2 squared. And that would be consistent with what we saw in part B as well, right? As long as the K that we had in part B matches this K here. So we might make a note of that. I came across another solution for this that's a little bit different, kind of a cool way to solve it as well. So I just wanted to share that with you too. This is the way that we've been solving these problems. We solved them yesterday, and a couple different times I've seen a solution that looks like this, but I saw an alternate solution as well. So I thought I would share that with you. And this really dives into the idea that we could have an equilibrium expression, which we've talked a little bit about for acids and bases. We haven't gotten to it yet in our lessons together, but I imagine you've talked about KEQs in your own classes at home. And so if we were to write a KEQ, if this is an equilibrium reaction, it must have a KEQ that's associated with it. That would be equal to products over reactants. So it would look something like this. And then we can rearrange this in a similar way that we did before to say N2O4 is equal to KEQ times NO2 squared, right? Just algebra there. And then we could plug that in for our rate law, and we're just continuing to bring this K2 that's down here. So this K is a different constant, again, from what we've had before, but because it's constant, we can say that it's that this is consistent with what the rate law was that we had before because of our concentrations of NO2. So two different ways to solve it. We haven't talked about KEQs specifically in class together, so I put this one second, but it would be an equally valid way for you to solve this problem, okay? Great. So like I said, we're going to get into collision model today, talk about some graphs that I think will look pretty familiar to you, but we'll just give them a quick overview and then look at a couple of complicated problems where we have a multi-step reaction, and then wrap up our conversation with some catalysts and how they would affect a solution or affect a reaction on a couple different levels. Okay. So the collision model is obviously has a lot to do with how molecules are colliding. So what we want to say, and this is very similar to the kinetic molecular theory that we talked about 2 weeks ago, for any elementary reaction to successfully produce products, the reactants must collide successfully so that we have some bond breaking, and those would allow for some bond making events. Okay. The key here is just making sure that we're always thinking about collisions of the particles with one another. Okay. And when we say successful collisions are those that have sufficient energy to overcome the energy barrier, which we'll call that energy barrier the activation energy, and that the collisions must have the correct orientation that allow bonds to rearrange. And that orientation piece is something that we haven't spoken about before. I think the sufficient energy thing will make sense because we'll spend a lot of time talking about temperature, right? And so temperature would be kinetic or be connected to the kinetic energy of the molecules. And so if the collisions are not strong enough, it makes sense that we're not going to have reactions. But those orientations are really a lot of times where catalysts come in, and so that's where we'll spend some time talking about that today. Okay, I want to share a resource with you that I use in my class a lot. It's a free resource. Teachers, if you're listening, I think that this is a great resource that for you students. This is something that it's free. You're welcome to look at it too. I will find myself when I have some extra time noodling around on my phone or on the interwebs, going to compound interest, or it's www.compoundchemistry.com. They're a company that makes a lot of different infographics, such as this one. I think they look really great. But what I really like about it is it doesn't just look pretty. The chemistry behind them is really solid. And if you were to spend some time diving deep, which I'm going to do onto this one specifically about chemical reactions, if you dive deep in there, I think that there's a lot of learning that's going to happen. It's not just looking pretty, like I said. Okay, so I'm going to break down each of the different squares on here for us, but I would encourage you, even just in your spare time, to go ahead and look around. You can follow them on the social medias, or just go to the website down here and see what you can find. So let's just dive real quick. This is a nice visual representation of what's happening with the collision theory. Okay, and what did we say? That the collision theory tells us that in order for a reaction to happen, so here's our products up here, and here's our reactants up here, here's our products down here. In order for them to happen, we must have correct orientation and sufficient energy. So as we look through some other parts of this, we're going to want to assess, does this allow for correct orientation? Does it improve correct orientation? Does it improve sufficient energy? Does it do both? So if this is a correct orientation and sufficient energy for these two to hit each other in order for this reaction to occur, here is an example of the wrong orientation, right? So if the red molecule is oriented the same way, but the green molecule is oriented in the wrong way, even if they hit each other with the correct amount of energy, it doesn't matter how often or how hard they hit each other, they have the wrong orientation, and so we would not have a reaction. Conversely, you may have some reactants that are going to hit each other with the correct orientation, but if they just lightly tap each other or they don't collide with enough energy, you're not going to have a reaction. Now, a fundamental principle here is that especially if we have gases, but even if these are solutions that are reacting with one another, the number of collisions, even at a low temperature, is astronomically large, right? And so when we increase temperature, there are more collisions, but there are orders of 10 to the 10 to the 10, 10 to the 20 collisions that are going to happen in any one reaction. And so it doesn't mean that every single collision has to be exactly successful, but anytime we can improve the orientation or improve the amount of energy that solutions have, then the percentage of collisions will increase for our reactions. Okay, so this is a really nice just kind of summary of the collision theory, and then we can talk about some of those factors that we discussed on Tuesday and how they will improve the rate of a reaction based on some of the fundamental principles of collision theory. So we talked about increasing the concentration of reactants is something that will increase the rate of a reaction. And what that does is it increases the frequency of collisions, right? So this is green. It has an arrow here to indicate that it increases the frequency. And that makes sense. When there are more particles there, we know that there will be more opportunities for collisions to happen. Now, it does nothing to guarantee anything about the percentage of successful collisions. We haven't increased the energy, right? We have not increased the strength of those collisions. So increasing concentration only increases frequency of collisions. It leaves the percentage of successful collisions neutral, right? There's no change that happens there. When we increase the temperature of a reaction, okay, and so here's a Maxwell-Boltzmann diagram that we've looked at a couple of times together. So here's number of particles, the energy of those particles. We could say here's the most probable amount of energy for the particles. If we were to say that the area under the curve here, the green spot, is the particles that have enough energy to react, well, what happens when we increase from room temperature to room temperature plus 20 degrees? What we've done is we've flattened this curve. Oh, there's a phrase we've used a lot recently, right? We've moved both the frequency, the most common number of particles, and we've lowered it because we have so many more particles over here, right? We still have some that are down here. We didn't just slide the whole thing to the right. We've expanded it in such a way that the apex will come down, we have a whole lot more particles at the higher end. And if we were to compare the green area here to the green area here, at a higher temperature, there are more particles that have enough energy for collisions. I'm sorry, for reactions to happen. So enough and more particles that have, there can be more collisions, right? And more of those collisions will be successful because they are moving faster, so they would have a higher amount of energy, right? So this line right here, which we're gonna see in a couple of minutes, is activation energy, right? We haven't changed the activation energy at all. We've just increased the number of particles that are beyond that activation energy by increasing the temperature and having more particles over here. Okay, so seeing the difference between these two graphs would be a really important thing. And this is a great example of how, you know, on like an essay type question, we could give you these kinds of graphs and ask you to explain them. Looking that up, this isn't an easy explanation. There's multiple steps that you would have to go through in order to explain what's going on there. All right. Increased surface area, we looked at this. We know that when we increase the surface area of reactants, that's going to increase the rate of reaction. And that, similar to what we did with increasing concentration, we increase the frequency of collisions. There's more opportunities for collisions, but we know nothing about we haven't necessarily increased the energy or the strength of those collisions. So more collisions happen, but the energy or the strength of those collisions stays the same. Here's increasing the pressure. So this is really increasing pressure by decreasing volume, right? So what we see here is the piston is compressing the gas particles into a smaller area. So of course that means we will have more collisions. If temperature stays the same, we are not going to have a different energy of collisions, but we would have them happening more often. And so that would increase the rate. Okay, so I'm going to just zoom back to this overall reaction or this overall sheet real quick. I skipped over Catalyst for right now because we're going to talk about it in a couple of minutes at the end of today's lesson, but just encourage you you can download these for free and see if there's anything in here that helps you to understand how collision theory connects back to the rates of reaction that we have spoken about kind of for this entire week. Okay, another kind of graph that we look at that I think is probably familiar to many of you is the reaction energy profile. Okay, and it looks something like this. What we're seeing is potential energy is increasing along the left-hand side of the graph like this. We typically would talk about the reactants on the left-hand side, the products on the right-hand side. There are versions of this where we switch it and we talk about the reverse reaction. I'm just going to talk about forward reactions for today. And we know that there is, if these are my reactants that are happening over here on the left-hand side, that we need to put some energy in to get them to this activated complex, where we have sort of bonds are starting to disintegrate, and other bonds are starting to think about forming until we get to our products over here. Okay, and so again, what we need to have here is some collisions that are increase the number of collisions so that we can get to our products over there. That's going to expect or necessitate that we get to a specific amount of what we call activation energy, right? And so if this graph is given to us, we'll see a couple in a minute, that where the scale is very specific, is delineated here, where we have numbers on our y-axis. We can calculate the activation energy by subtracting the energy here from the energy that was given to us at the beginning. So here we have the we could calculate the just the energy of the reactants, or just the energy of the products. The activation energy would be a subtraction, where we'd say how much energy did it have to begin with, and then we would subtract that from this energy up here. The second thing we would calculate from here is the overall change in energy, delta H enthalpy, which we will get into in a couple of weeks. And that would be calculated from just the reactants to the products. It's independent of what happened in between here, right? So if we just wanted to look at the reactants to products, we would just look at the difference between those two numbers right there. This is an endothermic reaction, and I know that this is an endothermic reaction because my products have more energy. We went up from reactants to products. My products have more energy than reactants, so that means that we would define this as an endothermic reaction. And then we could define this one as an exothermic reaction. However, some things are going to stay the same. This is still, we would calculate our activation energy in the same way from reactants, from the line that is extended from our reactants up to the line that's tangential to the top of our curve up here. And similarly, our delta H, our change in energy, would be calculated the same way, but here we can see that we went from reactants to products, means energy was released out into the environment. This reaction would feel hot because energy was given off. That means that an endothermic reaction would typically feel cold because energy is absorbed from the environment. Okay, and so being able to identify whether something is an endothermic or an exothermic reaction just from a graph like this is an important skill. This is something taken right off of a AP test, where we're looking specifically at an uncatalyzed decomposition of hydrogen peroxide. And we should just be able to identify that because the reactants are higher than the products, that this is an exothermic reaction. Okay, so energy was released. This is an example of how we don't have any numbers, so we can't really calculate this. We're not going to, there's no math that's involved here, but we are going to, we should be able to assume that this is endothermic in nature because of the difference here, that this line is going down. Okay. There is an equation called the Arrhenius equation that connects our rate constant, our activation energy, temperature, the gas law constant. This is something that's listed in our course and exam description as something that's really important for you to be familiar with. And I suspect that when you go into college, and if you're going to take some college level chemistry, or you are certainly going to go higher than Gen Chem in college, that a familiarity with this equation is something that would be important for you to spend some time with. I'm not going to do any problems with it today because the course and exam description does say this is not something that's going to be directly tested on the exam, right? So you're not going to have to do this this year in the exam. So I want to focus in just on the things that we would have to practice. However, the fact that we can connect activation energy to temperature, we can connect activation energy to rate constant, specifically using this equation. We've got just a constant here that's called the rate factor. I'm sorry, the frequency factor. This is not the rate constant, that E there. Another typo for today. You know what E is the base for natural logs. Apologize there. The other way that you will see this equation is rearranged, where we can compare activation energy for one reaction at two different temperatures. Okay, so if we had two different temperatures, they would have two different Ks, and we could either get to activation energy or we could solve for one variable if we had all of the others. So like I said, again, this is not something that you will have to do specifically on this year's exam. However, it is something that when you get to college, I want you to make sure that you've had a familiarity with and would know that you could refer back to this equation to solve for any of the variables that we've listed here. If we're going to move on to a multi-step reaction energy profile, it is very similar to what we saw for a single step, okay? We're going to read this from left to right in a similar way that we would read our steps from top to bottom. We're also going to notice that our slow step is going to be have a peak that is much higher because, and it's this high energy a high amount of activation energy that we're going to have to put in order to overcome get our reactants over this hump, metaphorically, that's going to make this a slow step. Okay, and so what we see here is a double hump because we have two steps. We see that this one is much taller because it corresponds with our slow step, and then the second one would correspond with our faster step. This is still an exothermic reaction, right? We have delta H of negative 285 because we're going from our reactants up here to our products down there. Okay, so this is, we'll look at a couple of examples of how we could look at this together with a catalyst in just a minute. I suspect that in your earlier chemistry classes as well, maybe in some biology classes where there's a lot of connection to biology, you've talked about some of the stipulations of what a catalyst does. We hinted at it yesterday, where we talked about catalyst is consumed in the rate determining step, but then is regenerated in a subsequent step. Okay, so it would appear as a reactant in a earlier step and then occur as a product later on. What a catalyst is going to do on a physical level is to increase the number of collisions or provide a reaction path with lower activation energy. So it's either increasing those the effective collisions, so it would be the orientation, or it's going to lower the activation energy, or in some cases it might do both. Okay, and so when we said on Tuesday that adding a catalyst to a reaction, is that necessarily going to increase or decrease the rate of the reaction? Well, catalysts are very specific to a reaction. So not every catalyst is going to, by its definition, increase the rate of a reaction if it can't do one or both of these things. So adding a catalyst that's not specific to the reaction that's given to you would not change the rate of reaction. Okay, so if we define this first graph, this is similar to what we looked at before. Okay, we have one line that shows our uncatalyzed activation energy. Okay, please forgive my my drawings in here. Trying to get a consistent drawing on Google Slides it's my best effort, and I tried it a bunch of times. So be patient with me, okay, guys. Here it would be our activation energy for the catalyzed reaction, and so we see that this amount is lower. Again, I'm doing very qualitative work here. We'll look at some quantitative in a second, just for to understand what would happen for. Can you identify, is this exothermic or endothermic? It's an exothermic reaction. It has less activation energy for the forward reaction, okay, for when it's catalyzed. So what we've done is we have the same reactants, the same products. Our delta H does not change, and that's a key part of a catalyst, is it doesn't change the overall delta H. We're still going to get the same amount of reaction, the same delta H out of this reaction. It's just the path by which it will get there is going to decrease. The energy we have to put in, the activation energy, lowers. Okay, and we can do a similar thing. My line is not quite as good there, sorry, for an endothermic reaction. And I just really want to point out to you that, yes, the activation energy has been lowered, but our delta H has not changed for a catalyzed reaction. Okay. So a question like this, this was a really cool, this was a free response question on a test a couple of years ago, where you were given 4 different diagrams and you were asked to identify the 2 that could represent a catalyzed and an uncatalyzed reaction pathway for the same reaction. Okay, so what they did, they separated out my lines from the earlier graph and then indicate which of the 2 diagrams represent the catalyzed and which is the uncatalyzed reaction. So take a second to pause if you need to and take a look at this reaction. And what I would do here would be to identify which reactions are starting and ending at the same place, because if they are starting and ending in the same place, then they could be a pair of reactions for the same reaction, right? So we're going to identify our delta H. So it appears that for these 4 diagrams, they all start in the same place, but clearly we only have 2 that are ending in the same place. So the difference between our reactants to products is the same for diagram 1 and diagram number 2, but we see diagram number 3 is much more exothermic than these 2 over here, and diagram 4 is endothermic compared to these. And a catalyst is not going to change our reactants to products, it just changes how they get there. And so we would do, to answer the first question, is we would say diagram number 1 and diagram number 2 are the way to go. Okay, they are the ones that represent catalyzed and uncatalyzed reaction pathway for the same reaction. And now the second part is to identify which one is the catalyzed reaction. Okay, and so what I'm going to do is going left to right. Here's our activation energy for the first reaction. Here's the activation energy for the second reaction. Okay, and what I'm going to say is that the activation energy for diagram number 1 is less than the activation energy for diagram number 2. And so diagram number 1 is catalyzed and diagram number 2 is uncatalyzed. Okay, so that's just very qualitative in nature, but we still can make some pretty good conclusions about what's happening in each of these diagrams, in each of these graphs. Okay, here's another way of looking at that same picture that we looked at earlier, where we're saying a higher activation energy is here. Oh, sorry, this is a Maxwell-Boltzmann diagram. So instead of changing the temperature, I'm sorry, this is a different graph. This is Maxwell-Boltzmann, but instead of changing the temperature and moving our red line over, what we're doing is we are lowering the activation energy. Okay, so again, we're comparing the area that's underneath this curve, and we're saying that a higher activation energy, maybe the normal reaction, would be right here. And so only these particles underneath the line would have enough energy in order to produce products. Whereas if we lower the activation energy by adding a catalyst, we move the line down here, and in this way, we have increased the number of particles that are underneath the line as well, not by moving our line when we increased temperature before, but by moving our activation energy to the left. So our conclusion here is that we have more particles that have enough energy to become products because we've lowered the activation energy. Okay, this is, again, a question that came right off of an AP test. If we are given a Maxwell-Boltzmann diagram of line A, line B, and line C, which line in the graph would you change to explain the increase in the rate of a reaction if the only change in experimental conditions is the addition of a catalyst? Okay, so does line A move, does line B move, does line C move? So if we're going to change temperature, that might be one answer, but this question is asking about catalyst, and what we're going to say is line B here would move to the left when we add activation energy because, when we add a catalyst, because the activation energy is less. Okay, so the answer to this is line B. Whoa. I don't know what happened there. Okay, let's look at some quantitative information here. 2 reaction diagrams represent the same reaction, one with and without a catalyst. We've separated them out. Estimate the activation energy for each process and identify which one involves a catalyst. So we can look at our activation energy here. We're going to quantify it. I'm going to estimate that we have about 32 minus 6. You can argue with my numbers there, but it's somewhere close to that. And we have activation energy of 26 there. I want you to notice that we're going to start at the same place. So this number, the second number, 6 and 6, better match one another. This is 21. You might want to say it's 20.5. I'm just going to estimate 1 beyond what's here. So I'll leave it at 21 and say that we have 15 joules here, which makes this the catalyzed reaction because the activation energy is lower. I'm going to continue to hammer home this idea that the delta H does not change. Okay, that tells us that this is a catalyzed versus an uncatalyzed reaction because the delta H has not changed there. Okay, here's a 2-step problem where we're doing a similar thing, right? Where we're asked, one of them is the rate determining step, compute the activation energies for the first step of each mechanism. So I would estimate these as 90 minus 10. I would estimate this as 80 minus 10, and so clearly the one on the right is the catalyzed reaction again. Okay, and then compare the second steps to the two mechanisms. Well, the second steps both look the same. They both have the same amount of energy. Okay. And just to drive home this principle, I hate to keep saying the same thing, but I do think it's really important for us to remember that the delta H, the overall energy change for the reaction, is not going to change. So I'm just going to continue to review that to make sure that these diagrams are showing that the same way. Okay. Now, in my research and in preparing for you guys today, I kind of put our types of catalysts into 3 different groups: binding catalysts or binding catalysis, acid-base catalysis, and surface catalysis. I think the first one is probably the one you're most familiar with in terms of your studies in biology class, and so that's really specific to enzymes. We talk about either the reactants are oriented in a familiar or a more favorable way in order to lower the activation energy. There's a lot of help in making the reaction happen a little bit more quickly. And that's where you see kind of your classic enzyme here with a substrate. This is right out of like an AP biology book, if we're honest. But a similar thing could happen where we don't have specific bond, we just have some sort of interactions. I'm calling these binding catalysts, where they are interacting with one another in order to make our products here, but we don't have physical bonds happening between each of them. Okay, and we would think about kind of enzymes working that way. An acid-base catalysis is either where we're going to add or gain a proton, and so this is a really complicated picture that I'll leave up here for a couple of minutes or a couple of seconds, that came out of a source down here, and what's happening here is we're breaking sucrose down into glucose and fructose. So another probably example of something that would happen in biology or happen in the human body, where an acid would be joined onto this oxygen right here, right? So when the acid would donate a proton here, right? That's what acids do. They donate protons to jump onto this oxygen right here. That's going to weaken the bond that's here and allow this dehydration synthesis to come in and to break apart our sucrose into glucose and fructose. So this is a process that happens on its own. There probably is actually another enzyme that helps it to happen, but this acid catalysis is going to speed up the process even more in the presence by putting this hydrogen here and weakening that bond a little bit. Similarly, this is a much more general equation for base catalysis. In the presence of a base, we have this base over here that's going to grab a proton, weaken the bond over here, which has impacts on all of the bonds up here as well. And so this would allow for hydrogen to jump in over here. And we went from our double bonded O to our hydroxide over here. Okay, and so this base is going to be reproduced at the end. So we still have this base that can go and repeat this process over and over again. And we would similarly, we'd have a hydrogen over here, this acid that's able to continue on this process over and over again. And that would be classic example of how a catalyst would work. Okay, so 2 examples, pretty complex examples, and I think for our purposes, probably remembering that, oh, hey, what do acids do? They add protons, or they donate a proton. They're going to add that proton specifically onto the substrate, and then in the presence of a base, a proton would be removed, because what does a base do? A base is a proton acceptor. Both of those are consistent with our discussion of acids and bases from earlier on in the year. Surface catalysis is something that happens a lot in industries, and is a really cool thing where we talk about there's actually the surface area of a substance, typically a metal, that is going to act as a catalyst, because it's going to go through some specific steps in order to help the bonds to rearrange one another. Okay, and so here's an example right off of an AP test, where we're looking at the reaction of nitrogen and hydrogen to make ammonia, and there's kind of classically 4 steps to a process like this. The first step is where we have adsorption. So the nitrogen gas is coming in here to interact with the surface of the metal right here. Hydrogen was coming in and doing a similar thing. We're going to activate this by both of these elements of both of these atoms. The second step would be activation by the bond here is moving from between the nitrogens to the surface of the nitrogens to the metal to the surface. Sorry, the nitrogen to the surface of the metal, excuse me. Then we would have a reaction between the nitrogen and the hydrogen. And then the last part is that it would release. So this is really happening only on the surface area of this. That's why it's called surface catalysis or a surface catalyst, where the gas or even a solution is coming in and interacting with the surface. Then we have a reaction between two things, and then they get released. The surface has not been altered at all. Here's another example of using nickel, and this is one where ethylene, which has a double bond, is going to interact. Both hydrogen and ethylene come into nickel. So we would have adsorption, we'd have activation, we'd have a reaction, and then we'd have a release of the particles over here. Okay, so two different examples of the surface catalysis there. One of the AP questions that I came across as I was preparing for today is a short answer. We haven't spent a lot of time with those today, so I figured I would throw one of these at you. Or we haven't spent a lot of time with those over the course of these 2-3 weeks we've been together. So I thought I would challenge you to think about this, writing a short explanation for either in support or disagreeing with this statement that adding a catalyst to a reaction mixture adds energy that causes the reaction to proceed more quickly. So this is something that a student might say as they're explaining catalysts to their little brother or little sister. Would they be correct or not? And how would you explain whether you agree or disagree? So take a second to pause and maybe write out your explanation. And I would say that I would have to disagree with this statement, that catalysts do not add energy to the reaction. There's one of two things that a catalyst has to do. It either increases the number of effective collisions, or it provides an alternate reaction path with a lower activation energy. So in order for a catalyst to be productive, it has to do one of those two things. If we're going to talk about adding energy to cause a reaction to proceed more quickly, well, what we're doing there is we're adding temperature, and energy is always associated with temperature, not with a catalyst. And so we would not want to conflate those two things. And so this would be a good example of where you could tell the person that said this, educate them up on how catalysts actually work. So that's the end of our lesson for today. A lot of theory here, and I hope it was helpful for you, where we looked at collision model. I would really encourage you to go back and review that, because it has a lot of applications in multiple different areas. Got into some specifics about catalysts. Those reaction energy profiles, I think, are pretty straightforward, but you may want to practice a couple more of those before looking at your homework for tonight. Practice problems. This is right off of an AP test. So take a screenshot of this, because it is multiple steps where we're looking at carbon tetrachloride. Okay, and how this graph should look familiar to you, a Maxwell-Boltzmann diagram, how it's familiar to you based on what we've looked at before. And say the question's asking you how to draw a second curve on the graph that talks about the temperature if the collisions happen at 30 degrees Celsius. Okay, and then the second question we have for you gives you a reaction mechanism, ask you to write the rate law. So here's a couple of reviews actually from our lesson yesterday, but then draw a curve. So we're going to draw one of those potential energy curves, one of those reaction curves that we've been looking at today, that shows a two-step process. Make sure that you include the enthalpy, the change of the reaction, and clearly indicate what the activation energy is. Give you a second to take a screenshot there. Okay, that's the end of our lesson for today. Thank you so much for joining us. Check out apcentral.collegeboard.org anytime you have extra questions. We've got lots of lots of resources there for you. If check out that compound chemistry as another one if you're looking for some nice diagrams and some infographics to look at. And lastly, but very importantly, make sure you're encouraging people to go to cb.org/tech for any help that they need getting internet or getting access to a device. Have a great day. All the snow melted here. If you were worried about me, no hats and gloves today. So we're going to go outside and enjoy some sunshine today. Hope you're having a great day, and we'll see you tomorrow. Take care.